All right, we're going to do an online inquiry on material testing. If you watch the videos, hopefully you can ask some questions in the Discord channel, and we'll be able to get through some of your eLab questions. Then you're going to try to attempt this material testing inquiry. We're going to use a virtual tensile tester. You can see the link right down here. This thing I found only works in the Safari browser, it seems like. So you need to be in the Safari browser to probably get it to work. If you don't have the Safari browser, you can't get it to work, then let me know, and I'll just put the graphs right in the Discord channel, and you can do all the inquiry based off the graphs that you need there anyway. Okay, so what we have here is a curve, a tensile curve, and this is a little different here. This curve here is not what we normally have. So if you remember, what we normally have is we'd have a graph that has stress versus strain. It's a stress-strain curve, and it looks the same. It looks basically the same. It goes something like this, and but this graph here that we have at this top of this page here is the kind of graphs you're going to get from this online tensile tester. It's actually load or force. This is force. Load is force. It's force versus the extension and how far it stretches something. So this is basically, it gives you the same kind of looking graph, but normally what we want is we want stress-strain curves, and you're going to actually have to convert like this, all this stuff, to stress and strain. So let's just talk a little bit about why normally we have stress-strain curves, and this thing here is a force elongation curve. The key is that if you if everybody in the world agreed to make the exact same shape of dog bones, we had like a specified, and we do have a specified length of dog bones are supposed to be milled to like a certain specification, but not everyone is always going to adhere to that. So if you had different dog bones and we're testing like copper, for instance, okay, if you use a force versus elongation graph like this one is here, you would get different graphs. You get different graphs because like the cross-sectional area of the dog bone would be different for somebody else, or the length of the dog bone would be different for somebody else. So you would do a load versus extension graph, and you wouldn't get the same graph if you didn't have the exact same specified dog bones. If everyone agreed to have the same specifications for dog bones, then yes, you could use a force elongation graph. But the way to get around this is if different people have different dog bones for copper, you can still all get the same graph if you use stress versus strain. Because if you remember, what is stress? Stress is the force over the area, and the strain is the elongation over the original length. So you'll see that on the top here we have force and the elongation. That's what this graph is right here. So, but a stress-strain graph is the force over the area and the elongation over the original length. So really a stress-strain graph is kind of a proportional for what kind of size dog bone you have. That's why it doesn't matter what size dog bone you have. Everybody's stress-strain curves for like copper or steel or whatever would be exactly the same because you're doing it as a proportion of like some, the length and the area of the dog bone. I don't know, hopefully that makes sense. So there are two types of graphs. That's my point. There's two types of graphs. There's force versus elongation. There's also stress versus strain. Generally, we're using stress versus strain because that takes all the different kind of dog bones out of the picture, and you get the same curve for whatever type of material it's made of. If you have force versus elongation, then it's gonna matter what size the dog bone was. Okay. I wanted to kind of explain that before we kind of got into everything here. Okay, so if you, let me get that out of the way. Sorry about that. If I can get it out of the way, it won't go away. It won't go away. Okay, can I shrink it? Can't even shrink it. Can I hit this? Okay, all right. All right, so on this page here, we're going to have a tensile test. We're going to open it up. There's needs to be only be in Safari. We're going to test 4 dog bones. And normally what we'd do is we'd print all graphs of each dog bone, except for the cast iron. The cast iron dog bone is very brittle. It breaks really quick. It has a yield point that coincides with the failure point. So as it's going up and it starts to yield and starts to go around that plastic deformation curve, it actually breaks. So it's not very impressive. I'll show it to you real quick, but you're not going to have to do any math or any graph on that on the cast iron one. We're going to have to do the math on all 3 of the other graphs. I'm going to do one of them completely for you right here in this video. You need to do the other 2. If you don't have a printer and you can't print out the graphs, then you can just redraw them, redraw them into your book. I'm still trying to collect the books at the end of the year. Hopefully we have a way to do that. I'll get back to you on that, but you still should be filling out your books. Okay, so all 3 of these graphs are force deformation graphs rather than stress strain graphs. Okay, and so we have notice also the units. The units are not, the force is not in pounds, it's actually in kilonewtons. And the extension or the elongation or the deformation is not in inches, it's in millimeters. So this thing provides us lots of opportunities to do a lot of math and stuff. So we're going to want everything. We want the extension to be in inches, and we're going to want the load to be in pounds. So we're going to have to do some converting and things to get the stress and the strain at various points. Okay, here's some important information that you need to have. The dog bone diameter, not the radius, the dog bone diameter is 0.197 inches. The dog bone or initial length is going to be 2.95 inches, just a little less than 3. Okay, so we're going to be using those. Here's some conversion factors. 1 inch is 25.4 millimeters. 1 kilonewton is 224.8 pounds. So we're going to use those to convert some things here. So the first thing we want to do actually is to calculate the cross-sectional area of the dog bone in square inches. So we're going to be using that in our math. So I think before we even get going on the test, let's just go ahead and do that math right now, right here. So what do we got? So if we're going to do that, we have the diameter was 0.197 inches. We can divide that by 2, and we get a radius of 0.0985 inches, right? And then the area, cross-sectional area is it's a circle, right? So it'd be pi r squared. So we're going to take pi times this radius here squared, right? And we're going to get a cross-sectional area of 0.0305 square inches. So you should write that down. You're going to use that in all three of your math things, and so that's all we really need there. Okay, for each graph then, we're going to calculate 6 things. They're right here. Well, there's 6 items, but there's actually a couple items in each one. So number 1, it says label the proportional limit on the graph and calculate the proportional limit stress, which is in PSI, and the proportional limit strain. The proportional limit and the yield point will be about the same point. So that's when you have a straight line going up, and then there's kind of the yield point, and then it goes on around like this or something. So right here, that point right there is what we're looking at. We want to calculate the stress and strain at that location right there. That's for number 1. Number 2 says label the max force location. That'll be like up here at the top. And we want to calculate the stress up here at the top also. We don't need to calculate the strain there, but we do want the stress. Number 3 says label the breaking point. Of course, the breaking point would be right here at the end. And calculate the breaking point stress and the strain. So here we want the stress and the strain. Right up here we wanted the stress and we wanted the strain. Okay. 4 says solve the modulus of elasticity. That is the slope of this line. So we want the slope of that line, and the slope of that line right there, if you remember, would actually be the stress over the strain. So we're going to take what we got in number 1, we're going to take the stress divided by the strain that we got in number 1, and that will be our modulus of elasticity for this one in PSI. The resilience. The resilience is the area underneath the triangle. So we have the line, we found the slope to get the E, but we want the area under here. So that would actually be, this would be the stress times the strain, and then divide by 2. It would be 1/2 base times height. So we'll take the stress times the strain in number 1, and we'll divide that by 2. 1/2 base times height, then we'll have the resilience. That'll also be in PSI. And number 6 is the reason why we figured out some of these other things. We're going to figure out the toughness, and here's the equation for toughness again, if you can remember that. So we'll maybe jump back and forth between these 2 screens and be able to test some things here. Okay. All right, so if you click on the virtual tensile tester and you're in Safari, it'll open up the tensile tester. We'll go ahead and do that. And here's what we have. And we have a graph, and you'll see it's load kilonewtons versus millimeters. And so we want to obviously figure out stress and strain on this. We don't want this graph. Here's the little pull aparter thingy. And here's our 4 different things we're going to test. So the first one we're just going to look at right here is the cast iron, because we're not going to actually graph or do anything with this, but I'll just show you what it looks like. We put it in there and we click start, and it starts pulling it, and see, it just breaks. So it fractures right away. So it didn't even, it just had a straight line up here. You do the slope of this to figure out our modulus of elasticity, but it breaks right where the proportional limit usually is supposed to yield, and then kind of have a plastic deformation curve here. It doesn't have any plastic deformation because it's very brittle. It didn't even do any necking or stretching there at all. So I just wanted to show you that graph. We're not going to do anything with that graph at all. So this is, let's see, this is copper. This is aluminum. I'm going to let you do those 2 together. This first one here is mild steel, and that's the one I'm going to do. So I'm going to put it in there. I can click start, and there it goes up, and then it yields a little bit, and then there's plastic deformation. It's necking down here. If you look, it's going to start necking, and then it fails. It breaks. Okay, and so we have this graph, and we have to do all of our work on this graph. I'm going to kind of blow it up here real big, so I'm going to do some drawing on it. Okay, so there's several things that we needed to do here. Remember, number 1, we needed to label the proportional limit, and that's, of course, at the end of the straight line at the beginning. Right there is the proportional limit. Up here is the ultimate tensile stress, and the maximum force is up here at the peak. And then right here is the failure point, and we had to label all of those things. Okay, we need to figure out several things, calculate several things here. First of all, let's kind of look at our graph and our grid and figure out how we're going to do things. So you'll see the extension down here at the bottom is in millimeters, and there's 5, and there's little lines there. That'd be a 1, right? That'd be a 2, 3, 4, right? 2. Okay. And so each one of those ones is divided up into 3 sections. So each one would be like a 0.33. So you have 0.33, 0.66, 1, 1.33, 1.66, and then 2, and so on. So we'll have to just kind of remember that. The load is even more difficult. You'll see that it goes up by 5 kilonewtons, but each 5 kilonewtons is divided up into like 3 sections, 1, 2, and then 3, right? So if you take 5 divided by 3, 5 divided by 3 sections, you get like 1.7. So each little grid going up is like 1.7. So we'll have to try to remember that and how we can kind of divide where it is. Okay. Problem 1. Problem 1, we're trying to figure out the stress at the proportional limit, and we're trying to figure out the strain at the proportional limit. Okay, so the stress at the proportional limit is equal to the force over the cross-sectional area. The force here, we're going to call it 30 to make it easy. It's going to be 30. 30 kilonewtons, right? So we need to convert that to pounds. So to do that, you take, you have 30 kilonewtons, and if we're doing dimensional analysis, we have 1 kilonewton was 224.8 pounds. Okay, so I'm going to take 30 times 224.8 to get that, and that gives me 6,744. And then I'm going to divide it by the area, which remember we already calculated was 0.0305, and that gives me then a stress of 221,000, and you should be checking all this math on your calculator. 221,115 psi would be the stress right there at the proportional limit. We also have to calculate the strain. What is the strain? The strain is the elongation over the original length. Okay, and the elongation here, if I measure over here, is about right this line right there. I'm going to say that's 0.67, right? So I need to convert that 0.67, that's 0.67 millimeters. I need to convert that into inches. So I'm going to do the 0.67 millimeters, do dimensional analysis. 1 inch is 25.4 millimeters. And that is going to give me, I think, 0.026 inches that it stretched. I'm going to divide it by the original length, which is 2.95 inches, and I get 0.0088, and there's no unit on the strain right there. Okay, so there's your strain, and there's your stress. That's the answer to number 1 with the proportional limit. So we want to remember those because we're going to use those two to solve some of these other problems here. Okay, I'm going to clear that out, and then we'll go into it again. Okay, so what's number 2? Number 2 is where's the max force, which we already labeled. That's up here. And I want to find the ultimate tensile stress. Stress, again, is the force over area. What's the force that I have here? We're going to call that 40. It looks like it's about 40 kilonewtons. And I need to take that 40 kilonewtons times 224.8 pounds to convert it. And if I do that, I get like 8,992 pounds divided by the cross-sectional area is 0.0305, which we figured out at the beginning. And I get 294,820 psi. That is the ultimate tensile stress for mild steel. Okay, that was number 2. All right, I think I can just erase all strokes. Hang on, that'll work. Okay, so now for number 3, I wanted to find the stress and the strain at the breaking point. Okay, at the breaking point. That's down here at the end. Let's see, what do I got? I have this, and I have this right here. Okay, all right. So what's the stress? So this looks like it's going to be, if I do 30.17 and then another 1.7, I'm looking at like 33.4 or 33.3, okay, kilonewtons. And I need to take that times 224.8, and I would get like 7,493 pounds. Okay, it's about 7,493 pounds. I divide it by the 0.0305. I'm calculating stress right now. Okay, this right here was about 33.3 is what I calculated that, kilonewtons. And of course, we took that times 224.8 to get it into pounds. So hopefully you followed that. Okay, so the stress right here at the failure point is like 294,820 psi. Okay, the strain, this would be 11.3 millimeters. We're going to divide that by 11.3 millimeters. We're going to divide it by 25.4 0.4 millimeters, and that's going to give us 0.445 inches of stretch divided by the original 2.95 inches. So this is in inches, this is in inches. They cancel, there's no unit. Okay, and so I get a strain at the failure point of 0.151. Okay, so there is my stress and there is my strain at this failure point right there. That was number 3. All right. Number 4 says, what's the modulus of elasticity, or Young's modulus, for mild steel? And to do that, we just take the slope of the line, and so that would be my E. The slope of the line, that's rise over run, that's stress over strain, and that'd be and we calculated those in the number 1. So in number 1, we have a stress of 221,115, and then we had a strain of 0.0088, and so if I just divide those, I will get my Young's modulus for mild steel, and Young's modulus for mild steel is about 2.8 million, like 2,763,938 psi. That is Young's modulus for mild steel. Okay, that was question 4. All right, question 5. You can pause this video if you're not understanding and kind of see exactly what we're doing, because you need to do this for your other 2 graphs to insert into your book. Okay, number 5 is calculating the resilience. The resilience is actually the area underneath this line. It's the area of this triangle right here. That's how you calculate resilience. And resilience is equal to 1/2 base times height, right? 1/2 base times height. And that would be then 1/2 strain times the stress, which we calculated in number 1. Okay, so I do 1/2, it'd be equal 1/2. The stress was 221,115. Times the strain was 0.0088, and so that would give me a resilience of about 973 psi. I really hope I did calculate all these out. So if you're going through this video and you find a mistake I made, please post in the Discord channel and I'll try to put a correction on there. But I think I did everything right. Okay, so finally we have the last question. Question 6 is calculating the toughness. The toughness is a big. Basically, the toughness is the area underneath this entire curve. Now we do calculus to do that. It's called finding the integral. We have to integrate underneath the curve. But what we're going to do is we're going to use a just an equation that basically, kind of predicts kind of what the area under that curve would be. So it's 1/3 times the strain at the breaking point or the failure point times the stress at the yield point, right? Plus 2 times the stress at the ultimate tensile point. So the yield point is here, right? The yield point's here. Right here is the ultimate tensile, and then right here is the breaking point. That's why we had to figure out some of those things at those places, all to be able to figure out the toughness. So you could put all the things you have. You have all these calculated. You put them all into the equation, and your toughness, at least what I came up with, I think was about 40,808 psi for the toughness. Okay, so that's how you do all 6 of those calculations on these. You need to do that on the other 2. So that'd be let's see, what do we got here? We got aluminum. I'll just go ahead and down there and put it in there, and I'll click start and show you kind of what the graph looks like. Okay. So there's the tensile test for aluminum, and you need to do all the math on that one. If you're watching this video, I guess you could pause it and actually just screenshot it right there, and you can have it if you wanted. And then also we have copper. I'll do the test on that. Copper goes way up, then it cuts basically straight across and goes down. Okay, so there's copper also. You need to figure out all those calculations for those last two there on your own. And good luck. Hope you can figure it out.